Hi, in this video we talking about the traveling salesman problem implementation, and I implemented it with simulated annealing. So first of all, the first class we are going to talk about is the city.java. Of course, it has a private string name. It is going to represent the name of the city. It's going to have an x coordinate, uh, and it's going to have an y coordinate. And the constructor gets a name, a coordinate x, and a coordinate y. It is a location, if it's not straightforward, so it's going to represent the geometrical parameters of the given city. We are going to create getters and setters for the city name and for the coordinate x and coordinate y. We are going to override the toString method, and we are going to implement the distance2 method. And it is basically the Euclidean distance. I'm not sure whether you are familiar with the Euclidean. I'm not sure that Euclidean. Or whatever, I'm not sure how they write it in English. Euclidean distance. Basically we calculate the x distance. We are going to subtract the coordinate of the city, that coordinate, and the city.get coordinate y. It's going to be an x distance, and we calculate the epsilon distance, and we're going to calculate the square root of their squares, and it's going to give the distance, and we are going to return this distance. So that's all about the city, and we are going to have a single travel. It is the tour that we are taking, and as we have said earlier, that for n cities, if we have n cities, we have n factorial permutations. So we have n factorial single travel or tour, whatever you prefer. So we are going to store the list of cities in a tour list. We are going to have a distance. It's going to be the overall distance. We keep going from city A to city B, from city B to city C, and we keep adding the distances between each pair of cities, and we are going to sum it, and it's going to be the final distance. So it's a distance, it's represent the distance of the whole tour, the whole travel, not the distance between given cities. It's going to represent the whole distance we have to take during our traveling salesman problem. So it's going to have a in the constructor we have to specify the number, the size of our single or tour list, or unless we would get a null pointer exception. So in the single travel manager, it's going to keep track of the destination cities and the number of cities. It's going to be static, and it has two methods, the add city. It's quite straightforward. We just keep adding cities at the destination city. It is an array list, and we keep track of the number of cities as well. So here we iterating through the number of cities, and the tour list dot add null. We keep instantiating our tour list. We keep setting it to null because we haven't visited it yet. Yeah, we are going to generate getters and setters for them. The most important methods in this class are the followings. It is the generate individual. We keep iterating through the number of cities. Single travel manager, as I said earlier, keeps track of the number of cities, and here we keep iterating through the number of cities and set the city to the given city. So the set city, as you see, that tour list set with the index city index, and we set the city. So all we do here is generate a a random tour, as I said earlier, because the main principle in the simulation is that at start, this is the solution, and in the algorithm we keep enhancing this initial solution, and we are going to talk about it later in the simulation, and this is why we set collection.shuffle this.tour. So with the help of shuffling, it's not my method, it is the method of the collections, we generate a random tour. As I said earlier, in the theoretical basis, we're generating a random tour, and then we keep getting edges at random, and we have to decide whether we have to swap those edges or not in order to enhance our solution. So this is when we generate the random tour, the initial tour. It's just getters and setters, as I said earlier. The get distance is the method where we get the whole distance of the given single tour or single travel. So if that distance equal to 0, we create a tour distance variable, and we keep iterating through the tour list, that size. It would be practical to say something like this: in that size, this that tour list that size, because Java in a for loop it keep calculating the this.tour list that size here. So in Joshua Bloch Effective Java pointed out the need to do so. I mean to do it like this. We keep defining the size, and we generate our for loop like this, because if we keep iterating through a database, for example, for Boeing or Lufthansa, where there are several millions of records, then we have to keep if you want to calculate the size of the list, it would be very, very slow and very, very impractical. But here, if we have 20 or 100 cities, it's not a problem, but I think it's a good programming practice to do it like this. Okay, so we have a from city. It's going to get city with the index I, and have a destination city, of course, and we just keep iterating through and calculate if I plus 1 is less than this.tour.size, it means that we are checking that we are on our tour's last city, and we are set our tour's final destination city to our starting city, because that's why that's the problem of the traveling salesman problem, that we start from a given point and we want to end up the same point. And else we just keep the destination city equal get city.null, okay, and get the distances between the two cities. We calculate the distance here, and we return that distance equals to tour distance. So here we just keep calculating the single travel whole distance, and it is important because we keep making decision according to this single travel distance, because we have to decide we keep generating solutions, and we have to decide which is the better, and we keep deciding according to this get distance, because if the distance is less, then that's the better solution, of course. Okay, and in the simulation, yeah, here in the single travel, of course, the toString method, I just created a temporary string variable, and just keep iterating through this tour list that size. It's not so efficient too. I'm not going to okay, I'm going to int size equals this that tour list that size, and here just says I less than size. I just keep concatenating the get city I, and it's going to put the name of the city there, So it is not so efficient because concatenation, we should do it with string buffer or string builder, which can do the string concatenation very, very efficiently. But anyways, it's going just for demonstration purposes. It's good. So in the simulation, as I said earlier, we created a double temperature. The temperature parameter is going to specify that what probability we accept the solutions. And we have a cooling rate because we keep decreasing the temperature with the cooling rate, of course. We have a single travel. And yes, we just initialize the initial solution, basically. And then initial solution, we just system it out to the console. We have a single travel, set it as the best travel. And while the temperature is greater than 1, we keep iterating, we keep running our simulation. So create a new neighbor tour. This is the new solution. Get a random position in the tour. This is the travel position 1. We keep using the mass.random to choose the tours and the travels randomly, and get the cities at selected positions in the tour. So we keep getting the cities here with the getCity method, of course, and we keep swapping them. So we keep calculating the energy, of course, and yeah, we keep calculating the energies. And as I said earlier, the energy is the get distance, so the distance of the whole tour. And I think it is just for historical purposes. We call it energy and we call it temperature because I think, first of all, these kind of simulations are used in physics-related stuff, physics-related simulations, such as I said earlier, the easing, how to simulate magnetism with the help of the easing model. So it's usually use energies, and yes. So basically, we calculate the energies and we keep making our decision according these energies, because yes, because we keep track of the best solution found here. We keep calculating the acceptance probability, and the acceptance probability gets an energy, a new energy, and a given temperature. The temperature is not a constant, as I said earlier. We keep updating the temperature. It's keep getting cooler and cooler. And if the new energy is less than the energy, as I said earlier, we accept it, because we accept it with 100 probability. I mean 1 probability, 100%, because mass.random generates numbers between 0 and 1, and if it's 1, it's going to we are going to accept the given solution, and else we return the mass.exp, energy minus new energy. So we see that as the temperature gets lower and lower, we keep rejecting worse solutions. And of course, if the new energy is greater than the previous, it means that it is a better solution. There's a higher probability that we accept that solution. But in order to avoid local minimums, as I said earlier, sometimes we reject the good solution and sometimes we accept the bad solutions, and this is what this mass.x function does in order to avoid local minimums. So if this is true, then the current solution is equal to a new single true, the new solution, of course, and we keep decreasing the temperature, of course, and we are keep track of the best solution found. So this is what we are doing here. The current solution that get distance is less than the best travel get distance, then the best travel is going to be a new single travel. It's going to be the best solution so far, so we keep track of the best solution. So basically, I think the theoretical background of and of course we can test it. I'm going to test it with 3 cities. It's not so initial solution, yeah, and the final solution is there because there are not so many permutations with a given number. I mean 3 cities. We should use it with 20 or 100 cities. It is up to you. You are going to test it whatever you like. Budapest, London, Berlin is the sequence, of course. So I think the theoretical background of this kind of simulation is very, very easy, very, very straightforward. And this is why these kind of simulations are getting popular and popular nowadays, because you don't have to, it's very, very easy to implement, and it's quite straightforward what we are doing. We keep accepting, we just have to, and it is a basic principle. These kind of algorithm was created by mathematicians and physicists. We just have to take it for granted that it's going to work, and the implementation of the given algorithm is not so hard to do. So thanks for watching. This was an extra video on this traveling salesman person problem. Thank you for watching.